Let's take a few minutes to think about how pointers and addresses and things like that work. A pointer in C++ is an address. So it is the memory address or the location of some, say, variable or object. Addresses are integers in that if you have the addresses of memory, a memory address, it goes from 0 to some maximum value. If you're talking about 32-bit processors, that is about 4 billion, a little bit more than 4 billion, because you can have 4 gigabytes of memory. So each address refers to 1 byte in most processors that we use these days. However, and so before I forget, addresses are not negative. You can go in the negative direction, but there is no negative value for an address does not make sense. They're all positive. So even though an address is, you can think of that as an integer and a pointer is an address, it turns out a pointer is not an integer. And this is not crazy. This is the way to think about pointers. C++ forces pointers to be used as addresses, but it cannot be used as numbers, even though technically it is a number. So let's take a look at some of this. Let's say we have x is equal to 5, and then we have, let's say, set up a couple of variables, int star y, and let's say we print out x right away, and then let's say we have two variables, y and z. Print out z and the rest of this. We know what this will do. Okay, first of all, you want to take a look at this statement, int star y z. And if you're not sure, try it out. What exactly is z? It might look like we're saying z is a pointer to an int, but no. Turns out z is just an int. So remember, we went over that just very quickly before. Pointers are declared like other types, and you add a star before the variable name. It doesn't matter where you put it, actually. You can put it right next to the int, but it doesn't change the fact that this star actually goes with the y. So if you want to make z a pointer, you have to do that. Alright, so that's one thing to keep in mind. Now, unlike references, you can say at any point in time you can change the value in y. Y is right now, it's not initialized, so it can be anything. And so let's say we initialize y to point to x. So this is saying y will have the value that is the address of this variable x. And let's print it out. Alright, compiles and runs. Okay, so this is all fine. Now let's print out y as we did before, but without a star, that is without dereferencing. Okay, and we get this is the memory address of x, because we know that we set y, the value of y, which is an address, will be the address of x. And it turns out this is the address of x. Now, what we want to do is we want to say y++. And this is a thing that you can do in C++. Try to save it, compile it, it should compile. This tells us that this is allowed. We have a z that we haven't used, so that's okay. Now, let's say we print this out. Okay, so we print out y, it's the address of x, and then we bump up y. So you want to think about this and see what it does. If you want to think about it for a second, you can pause the video, but I'm going to go ahead and compile this and run it, so you might want to pause the video now. And notice what it did. So this, we haven't talked about exactly what this is, but this is a hexadecimal value, that is base 16. We don't need to know exactly what the value is, but notice at the very end, this ends in a 5-4. Actually, the 4 is all we need. We bump it up by 1 and it goes up by 4. So this is called pointer arithmetic. That is, when you use pointers to integers or pointers to int, it knows that the C compiler knows that ints are 4 bytes long. So when you do a y++, pointer arithmetic rules say that you will point to the next int, which is 4 bytes away because each int is 4 bytes. That's why it goes from 54 to 58. Okay, so although it looks like it should bump up y from 54 to 55, nope. The way pointer arithmetic works, and you can do pointer arithmetic in C++. Definitely, this is something you cannot do in Java, right? And so when you do pointer arithmetic, the rules are slightly different. This is overloaded for int stars and so on, so that it goes up by a value of 4. Okay, so keep that in mind. Remember that the star goes with the variable, even though it is, you can read it as p1 as a pointer to int. This star goes with the variable name. So v1 and v2 are just regular ints. Even though addresses are integers and a pointer is an address, pointer, you don't want to think of that as just a regular int. And you can see when you for example increment it, it goes up by 4, not just by 1. It's one of many ways in which pointers don't really behave just like integers. Okay, another thing that we will talk about is pointing to. We will think of arrows rather than actual addresses. We won't think of addresses much. Every once in a while we'll look at them. There's no real advantage to printing out pointer values. Like there's not much of an advantage. Sometimes when you debug you might want to know about this, but most of the time we really don't care what this value is. We just treat it more abstractly and we talk about pointing rather than addresses. If you're dealing with assembly language, sure, you want to talk about addresses. Okay, pointer variables point to ordinary variables. So an int star x or int star y will point to a variable of type int. We leave out any talk of addresses, usually. And so we sort of view in our mind's eye, we see memory references as arrows pointing to some location. Now this will be extremely important when we look at dynamic data structures such as linked lists and trees and things like that. So all of this stuff is not just notation, but it's something that's very useful for later chapters when we talk about complicated data structures. Okay, we've done this kind of thing. We can say int star p and also declare a variable v1, which is of type int. Remember, the star goes with the variable name, and so we can say that p1 will have the value which is the address of v1. And so from now on we won't say that. We will say that p1 points to v1 as much as possible. We'll try to do that. This operator, this ampersand operator, used as a prefix, used in prefix form, says that this is the address of, or the value of this whole thing is the address of this variable that it operates on. And the way you want to read this is p1 is assigned the address of v1, or you can say p1 points to v1. Okay, so now we can refer, if you have something like this, just like with references, sort of, you can say that there's two ways to refer to this variable v1. One is to say just v1, the other one is to say, oops, this is missing a less than, cout less than star p1. So we can refer to v1 via this pointer p1 or by the name v1 itself. This star is, as we mentioned before, it's the dereference operator. We're saying that we're going to dereference, another typo, this should be the pointer variable is dereferenced. Or the way that I like to think about it is when you have something like this, you're saying cout the data that p1 points to. Okay, once again, we need a less than or insertion operator right here. Okay. So okay, here it is. So when we see something like this, we want to read this as get the contents of memory that P1 is pointing to. So P1 and V1 are two ways of referring to the same memory, that is V1. Refer to the same variable. This address of operator is also used to specify pass by reference or call by reference parameters. That's no coincidence. That's how C++ was designed. Remember that call by reference parameters pass the address of the actual argument. All right, so this should, if you remember call by reference, this should all make sense. And the use of this operator, this address of operator, these two uses, that is for address of and call by reference or pass by reference, are closely related. If you have two variables, both of type pointer to int, and that's what this is declaring, you can assign them to each other. You can say P2 is equal to P1 or P1 is equal to P2. And when you do P2 is equal to P1, you want to read this as P2 will now point to the same thing where P1 points. And this is different from star P1 is equal to star P2. This is saying whatever, so the way I would read this is whatever P1 points to, in that memory location, store whatever P2 points to. So another way of saying is assign the value pointed to by P2, take that value that P2 points to, assign it to the value pointed to by P1. Okay, and you want to go over this example. You can pause the video if you want. If this goes over the picture, oops. When you have an assignment like this, P1 is equal to P2, assuming they're both pointers. P1 points to the 8, P2 points to the 9. After you execute, this is before you execute this statement. After you execute the statement, P1 will just point to the 9. Now this is different from star P1 is equal to star P2. So we're assigning the value that P2 points to, which is 9, to the value that P1 points to, which is currently 8. So after you execute this statement, the thing that P1 points to will now be 9. They will both be 9. So it's two very different things. If P1 and P2 are pointers, you can assign pointer values. You can also assign the values that they point to. Alright, next up we will take a look at the new operator. So you've seen this in Java. It's essentially the same thing. This allows us to allocate memory from the heap. And why would we want to do that? Because it's a lot more permanent. It'll stick around even after you exit a function, for example. So you can allocate memory in a function and then leave that function or return from the function, and that memory will still be allocated. And that is both a good thing and a bad thing. It can be a bad thing if you don't deallocate that memory in C++, and that's going to be a big part of the next couple of videos.